Now, this last process I would like to talk to you about is scattering. Scattering is any process that changes the direction of a photon. We talked about absorption, which extinguishes the photon, and we talked about emission that adds a photon. Now, scattering is a process that is not destroying or creating a photon, but it's changing the direction. Now, because we described the radiation field in terms of intensity, which has an explicit dependency on direction, a scattering event means that the energy was removed from a beam and joined another beam. If you are following the beam A, what you are seeing here is an absorption. And if you're following the ray B, what you're seeing here is an emission. That means that you can treat a scattering process as an absorption process plus an emission process. So let us parameterize the absorption part in terms of a scattering coefficient, sigma. So let's treat that as we would treat an absorption. Di is equal to minus sigma rho I. Now, the scatterers in stars are mostly non-relativistic electrons, and for this, the scattering is isotropic and coherent, meaning that there is no change in wavelength. The scatter is elastic, meaning that the ensemble of electrons do not gain energy or jump quantum states. Now, because scattering conserves energy, the photon that was lost from one direction will be found in another, so the total energy absorbed must be equal to the energy emitted. That means that if you integrate over all directions, you're going to find the photon. So you can write this expression that the directional integral of all of the absorption events must be equal to the directional integral of all of the emission events related to scattering. Let's call the emissivity J scattering. So on ray A, you had an absorption, and on ray B, you had an emission. We're giving the superscript S just to show that this is a scattering emission, not a true emission. What this relationship is saying is that if you integrate in all of the directions, the photon that you lost by scattering from one beam is going to be found in some other beam. Now, if the scattering and emission are isotropic, then we can remove these coefficients from the integral. The density is also considered isotropic, so we can remove them from the integral too. Now, if you isolate the scattering emissivity, and we recognize the fraction of integrals as the mean intensity. So we find an expression for the scattering coefficient. So we found the scattering coefficient for isotropic scattering. And let's bring back the subscripts of frequency. So this relationship is telling you that the scattering emissivity is proportional to the scattering coefficient. So in fact, you only need one coefficient. You only need the scattering coefficient. You do not need this scattering emissivity. So based on this, you can write the equation of radiative transfer for pure scattering. You had that di was equal to minus sigma rho I plus j s rho. Substitute that by the mean intensity. Oh, since that I forgot a path here, of course. So this equation becomes di ds is equal to minus sigma rho times I minus j. Now let's reinstate the true absorption and the true emission. For the true absorption, you have minus kappa rho IDS. And for true emission, you have di is equal to j rho ds. Now, write the j in terms of Kirchhoff's first law. Imagine that you have a black body. J is equal to kappa times b. So you can write the emission as kappa b rho ds. And now add the scattering to it. If you combine all of these into a single equation, now if you group the positive terms and the negative terms, now restate the frequencies. If you compare this to the original equation of radiative transfer without scattering, you see that the equations are very similar, and you can actually define an effective opacity, which is a true opacity plus the scattering opacity. This is also at times called the extinction coefficient. Likewise, you have also the effective emissivity, and together you can define an effective source function. Now, let me again drop the frequency subscripts for clarity. And see here that you can define a quantity so that you can cast the source function in terms of this quantity. So this quantity relates the scattering to absorption and is called the albedo, the same albedo that I had heard before, which is the scattering over the extinction. The albedo varies from 0 to pure absorption. That means when you have no scattering whatsoever, to omega equal 1 when you have pure scattering, when the true absorption is equal to 0.